This video will continue our discussion of the directional derivative. So given the same scenario that we had in the last video, we have a unit vector, and on the screen is the definition of the directional derivative in the direction of u. So what I want you to notice here is we actually could rewrite this as maybe a vector in terms of our partial derivatives and dotted with my unit vector. If you notice, if I do that dot product, I get exactly to that actual definition. This is going to lead us to define maybe what this thing is. This calculation, this vector, actually is going to open up quite a bit in application for us. And whether there's a giant application, and I'll have in Blackboard or in person showing you what that is going to look like, depending on how you're taking my course. Now, this first vector here, we know that the second vector is just the unit vector, right? It's the same thing. We defined it up there. This, we're going to write it with the upside down delta there. I think it probably has a real name, but I'm blanking. We call it del, and it's del f. The name of this piece, this calculation is the gradient of f. We also call it del f. I don't ever call it del f. I just say the gradient of f, but curriculums do call it del f. So I can find the directional derivative. I have a new definition here. The new definition is directional derivative of f x y is equal to del f, or the gradient of f, dotted with the unit vector. All right, we also need to go ahead and give a definition, a formula for the gradient of f. The gradient of f is f partial to x, I, plus f partial to y, k, j. Woo, j. Right? Let's note a few things here. Here's our two definitions that come from this discussion. A couple things. The directional derivative is a slope, right? A slope, which would be a scalar, not a vector. Oops, I'm running into my own definition. Not a vector. Right? Gradient of f is a vector, and it relates to the grade, or the climb, relates to the climb. I guess we call it grade. Not a lot of people ever remember what that means. Grade of the surface. Okay. So a couple of properties of this thing, and then I'm going to prove the big thing to you of that we get from this. Okay, so properties of gradient of f. If the gradient of f equals 0, then the directional derivative equals 0. Just think about the definition of our directional derivative here. It's a dot product. So if it's a 0 vector and I dot it, the 0 vector with any vector, I get a 0, right? Almost a 0 vector, but dot products give us scalars. So we get a scalar. It doesn't even matter the direction because we're dotting it with 0 vector, right? Here's the big thing here. The directional derivative has a maximum value, right? The maximum value is the gradient's magnitude. And this happens when the gradient runs in the same direction of your magnitude. Your gradient runs in the same direction of the vector that's in question, right? I'm wanting to find a derivative in a certain direction. It would be the direction of the gradient. That is the maximum value when I take its magnitude. Now, what does that mean? Well, that means that is the steepest or the quickest way out of an area. Meaning if I have a surface, right? If I have like a valley and I put a point in that middle of that valley and I have an equation that represents that valley, right? A surface, I can find the gradient of that surface at this point, and it will point in the quickest way up or quickest way down. it will point in the direction of the most change, most increase or decrease, right? Decrease typically goes, well, if I'm thinking magnitude, it's always going to be positive, so usually we think increase, but we could put a negative and make it a decrease. Okay, let's look at why this is. Let's start at the directional, with our directional derivative definition. The directional derivative definition is the gradient of f dotted with u, right? If we remember this back a ways back, we have the definition of the angle between two vectors had a dot product in it. If I solved for the dot product, I then could say, hey, that's the equal to the product of the magnitudes of my vectors times cosine of theta. All right. Now, I want you to think about cosine of theta. Cosine of theta has a range, right? And cosine of theta is stuck between -1 and 1, right? Since it is stuck between those two, we have a maximum value here. Okay, let's think of a couple things. The directional derivative, okay, this is equal to it's the magnitude of the unit vector, so that's just a 1. So this is equal to the magnitude of f gradient of f times cosine of theta. Okay, well, I want to think about, okay, the biggest cosine can be is 1. So I'm going to assume that's 1. So if the biggest the cosine value can get is a 1, the biggest the directional derivative can get, right, is the gradient of f. The directional derivative has to be less than that. So the most it can be is the gradient of f, because the biggest cosine could be is a 1, putting it times 1. Now, if I think about that, that has to happen for cosine to be 1. For cosine to be 1, that tells me that theta has to be 0. So the angle between the gradient of f and theta, the unit vector, so angle between gradient f and u is 0. Thus, the gradient of f is parallel to u. That was that second part. So the first part, this was the big conclusion here. We have that. The biggest that the directional derivative will be is the gradient of f. So that means the quickest way up, all I got to do is find the gradient, the magnitude of the gradient of f. The vector itself tells me which direction that happens in. So let me get that across again to you again. The biggest the slope will be the magnitude of the gradient of f. That's the biggest the slope will be. The increase from whatever point you're at, the biggest increase will be that. Now, if I want the direction that is happening, the gradient of f is a vector that tells me what direction to go. So this gradient of f would be like in the xy plane, but it says, hey, if you go this direction, you're going to go up the steepest hill you can from that. It's the quickest way up. All right. And then the second part said this happens when they're running in the same direction. And that proves our point, right? That it is the max when we are going along the gradient. That was that second point. The first point is the slope, is the magnitude. The second point is it happens in the direction of the gradient, right? What's great about that is if that gives you your biggest value, then our smallest value is going to be the negative of the gradient of f. That logic works the same right here. If I want the smallest it can be, it would be when cosine is -1. That is, again, the opposite direction. So it would give the negative. So negative magnitude of the gradient gives you your minimum value. The killer here that's used everywhere is the gradient of f gives the vector for the steepest grade of a surface at a point. It's the quickest way out of wherever you are. Okay, let's find some gradients. Calculating them is not too bad. the concept is giant. Okay, so the gradient of f, they gave me this function. So all I need for the gradient, remember the gradient of f is partial of f with respect to x, partial of f with respect to y. So there's my gradient of f. So I need both of those. So I'm going to, I have f, I have that. You can do this multiple ways. I think I am going to rewrite my function. You could use the quotient rule if you wanted to. I avoid that. I'm going to do that instead. All right, so the -1 comes down. I got the inside is left alone. I drop my power, which is -2, and I multiply by the partial derivative with respect to x of the inside, which is going to be 2x. This ends up being -2x over x squared plus y squared to the second power. Now, you could do this again, right? You could do it with the y. But if you look at how the function is set up, there really isn't a difference here between x squared and y squared. The derivatives are going to act the same. We get the same kind of setup. So instead of doing all that work again, I can see that this thing is going to be -2y over x squared plus y squared squared. And this is due to symmetry. That's what we call that. I know, like, some of you guys are like, you could just tell. And I know maybe some math teachers in the past were like, well, you need to show the work. No, this is cool. This shows the work of it. The second part is just saying, hey, I understand how the mathematics works. I'm going to go to symmetry there. Okay, so we have that, and they just want to know what is the gradient of f plugging in 1, 2. So I'm just going to plug in 1, 2 into that first function. I got -2 times 1 over 1 squared plus 2 squared, all of that squared. Then the second is going to be -2 times 2 over that same thing. That's it. Yep. So the gradient is equal to, okay, the bottom is going to be 1 squared plus 2 squared. That's 25. So I got -2 over 25. And then I got -4 over 25. So that is the quickest way out. It's the steep incline up. I would go from 1, 2, and I would walk in the direction of that vector, and it'd be the steepest route up. Right? If I wanted the minimum, I'd just go the other way, opposite direction. All right, I got one more example of this here. Again, our gradient definition, we'll write it here just so we have it. It's partial of f with respect to x and partial of y, f with respect to y. So we're going to find fx. All right. We could do, I think quotient rule is actually okay here. It's not as bad. Notice there's an x, y, and z here. I didn't notice that when I was setting it up. Should have, since I wrote it and I just looked at it. The gradient just adds that third component. Now, it may not geometrically make much sense anymore because our vector, it's in 3 space, but still kind of interesting thinking about the geometric approach of the gradient being the steepest when we're talking about a 4-dimensional figure. Okay, so we have the gradient of that function with respect to x. So I'm going to do low d high. I'm going to actually write this out. Partial with respect to x, low d high minus high d low, all over low squared. All right, so let's see how this works out for us. All right, I got x plus z times 1. That's that partial derivative. Then I got minus, and it's the same thing there, but I got minus x minus y over x plus z squared. That is going to give me a z minus y over x plus z squared. Now, just like that last problem we used symmetry, we probably don't want to use symmetry here, at least not for our y. You can tell that the z may turn out the same, but I'm still a little unsure on what to put where there. So let's keep going. We got the y one. Now, I only have one term for y, so I'm going to write this function a different way. Here's a little trick to help you out with your derivatives. This is x over x plus z plus y over x plus z. The first term with respect to y is a constant, so I get a 0. The second term, I just get 1 over x plus z. It's nice and pretty, but that's focusing on the function being right here. Right? Splitting them up like that, I can do it nice and easy with respect to y. Right? Z, I could do that same thing. Well, there's Z on both. That doesn't really help us. Let's try it, and then we'll compare the symmetry question. So it's going to be low, D high, but now it's in terms of with respect to Z. So I'm really just copying down what I see above here, but I'm going to replace the partial to x with Z. Kind of speeds things up for us. Okay, there we go. So I got x plus z, and then the partial of x plus y is a 0. So I got 0 minus, all right? And then I got x plus y times that thing, partial of z is going to be a 1. And I got that over x plus z squared. So I don't think I would have guessed what I thought unless I made a mistake in my reasoning. But I don't think I would have guessed negative x minus y. I would have somehow. So symmetry in that case wasn't totally the same. And I think the reason being is because the x had an x on top and on bottom. The z had a 1 on the bottom only. And the only reason y worked out so well is because it was on top. Okay, I got one more thing to add to this video. Our book commits a whole section to this. I don't feel the need to do a whole section based on this. Maybe I'll change my mind. Maybe when you're watching this video, you get assigned this section after it. Well, you just get to see it twice. I'm only going to do a bit of lip service because it's pretty straightforward. So we have two different things here that sometimes we're interested in. There aren't very many applications for it. But tangent, well, I'm speaking out of ignorance there. I'm not sure. I haven't seen very many applications for it, so I may be wrong there. But definitions of tangent plane and normal line. So this is using if I take a surface, remember surface is going to have like x, y, and then a z, and z is our output. If I take that output and call it z and I set it equal to 0, creating a new function, right? We have done that in a previous technique. If I create a new function there, then we can get a tangent plane to a point. Now, the tangent plane is used using the point. Remember, for a plane, we need a point and a normal. Well, the plane through P is normal to my gradient. So if I find my gradient using this definition of trying to get it equal to 0 like we did above, then that is my tangent plane. You can see a picture right there to the side. Right, the blue there is the tangent plane. The gradient of f is sticking straight out. Okay, and then we also have a normal line having the direction of that, if we want it, is called the normal line. So it would just be taking your gradient, using the gradient as your directional vector, and that is called the normal line. So those two definitions, I may throw a problem or two at you on this. Other curriculums don't spend as much time on this thing as this book does. So we'll just cover it right here. That is the extent of that section. We did not finish the problem above, and thankfully I caught it before I stopped the problem. This says find the gradient at 1, 2, 3. To help with speed of this video, and you're not sitting here forever watching me calculate, you just plug x, y, and z into all three, and you should end up with a 1/16. Hold on, let me make sure I have the same problem in my notes. I do. 1/16, 1/4, and negative 3/16. So once you plug all that in, you'll have that there.